So I'm Simon Moore. I'm filling in for Robert Watson, who will be here later. Robert and I have basically done a sort of, I'm a wear a hardware hat, and Robert's worn a software hat doing the CHERI stuff since 2010. We've had lots of sponsors. So basically, back in 2010, we started looking, if you just take a clean slate, how could you design a computer that's fundamentally more secure? We really started looking at memory safety, and here's a couple of reasons why. Ian Levy, who is technical director at NCSC, says, buffer overflows have not objectively gone down in the last 40 years, and the impact of buffer overflows, if anything, gone up. And similarly, we see the same sort of thing from Microsoft. They've reported, in all their vulnerabilities. I should say this should be motherhood and apple pie for most of you, but as you see, there's some new people in the audience, so I'm hoping this is helpful. This is not just a Microsoft thing. Google report the same sort of things with Chrome. Let me just give you a very quick example using an XKCD comic of a memory safety vulnerability. So this was the Heartbleed bug from a few years ago. I like to show it because it's relatively simple. So this is the TLS protocol that's used to secure web transactions. And this vulnerability allowed banking systems to be broken, anything that does secure-based web stuff. Also allowed people to impersonate servers and all sorts of things. Pretty big bug. There's also one of those classic examples where the security analysis had focused on all the crypto and all that sort of side of things, but there was a little heartbeat message that went just to keep the TCP link alive. And basically, the attack runs as follows. So to begin with, the client says, hello, potato. You still there? Say potato. And the server says potato. And then, client says, okay, sort of 30 seconds later or so, you still there? Say bird. 4 letters, says bird. Then the client gets a little bit too evil and says, hello, server. Say hat. Trust me, it's 500 letters long. And it just reads out the whole buffer. And in there, you end up with key information and all sorts of stuff. I mean, this is absolutely nuts. But this sort of thing happens all the time. The question then is, well, what can we do about it? We are seeing the emergence of memory-safe languages. This is great. We really encourage people to use memory-safe languages. But I think we'd argue it's kind of tricky to port vast amounts of legacy code to a memory-safe language. It comes with a real cost. Really, our approach is how do we take your existing C and C++ code and also take your Rust code and make it even more secure, recompile it, and get a lot more memory safety. And so that's been our approach. So how do we do it? Well, CHERI is a modern capability architecture. There have been capability machines in the past. In fact, Intel's very first 32-bit processor was a capability machine, but it was horrendously complicated. So we've really taken a sort of reduced instruction set computer type approach, relied much more on the compiler. And this has gone from early work on CHERI MIPS in the sort of research phase of this. Then during the Digital Security by Design program, worked extensively with ARM. ARM did an amazing job to produce the Morello prototype, and there are about 1,000 units. Lots of people have had access to that. We've also, on the research side, started moving to RISC-V, and we actually had some DARPA funding to do that, and been doing things with Capabilities Limited and releasing open source cores, and taking lessons from Morello and pushing it into that space. We're now in a sort of the end game, really, of a standardization process. And it's great to see companies like Codasip have announced products, and SCI Semi, who are here today, and so on. And we also hope in the future that lessons from RISC-V will then end up in a future ARM product. So the crux of what we add to the processor is a bit like adding a new data type, a bit like adding floating point. We add a new data type to represent pointers. And a capability pointer includes a 64-bit address, but it also has bounds and permissions. And we also, in the instruction set, ensure that you can only use these capabilities in quite constrained ways. So you can use them to reference memory, you can manipulate them, but you cannot increase your bounds and permissions. And that's absolutely critical to the security argument. To ensure we have provenance, we do have a hidden validity tag, which we now know how to deal with on the hardware side. And that's critical for the security argument. So we know what is a capability in memory and what is not. Okay? There is no crypto required, which is interesting. So a lot of people think you add security, you've got to add crypto. It's like, there is no crypto in this. Okay. We extend the integer register file. They can store in capabilities in memory. We also add them to the program counter. And the tagging in memory protects them. And we add just a few new instructions to deal with manipulating capabilities and how do you access memory. I'm not going to dive into the details. We're sort of running out of time. So with this new capability, from a software perspective, we now get key properties. So we get integrity and provenance of our pointers. So invalid pointers can't be used. And this is for both code and for data. So for instance, we can mitigate return-oriented programming attacks by turning return addresses into capabilities. And if you accidentally overwrite a return address with some data, it is no longer a return address. It is data. It is not a capability anymore. We get bounds information so that you can constrain, It also means when a programmer allocates an object and you've got a reference to that object, you can't use that reference to access another object, which, so you get the sort of intent of what the programmer wanted when they wrote the code. You get this monotonicity property, so you cannot increase your bounds and permissions. Permissions, read, write, execute, but also whether you can store a capability there, and so on. So this gives you memory safety, and that's the sort of low-hanging fruit, if you like. You recompile your code, it becomes memory safe. Then the next really big win is compartmentalization. And this is where people more recently have been exploring this. And this is a very powerful technique to break your code up into smaller pieces and reduce the privilege needed to execute those pieces of code. And that fundamentally improves security. So we might have one protection domain A, and within that you've got a set of capabilities. So if you started with one capability, what can you reach within that region of memory? And within that set of capabilities, that will constrain what you can see. And given you can't take a capability and increase your permissions, you can't break out of that set of capabilities. So we could have, two different protection domains, and we can also have some flexible sharing inside. And you might, for instance, with the flexible shared area, not allow capabilities to leak, only share data. And you can do that with appropriate permissions. So this then gives, you can then use compartmentalization extensively. So in something like your Chromium browser, where each tab runs in a separate process at the moment, we can now use CHERI compartmentalization to protect things. But you could also take it further. Process-based compartmentalization just doesn't scale, whereas CHERI compartmentalization does. So not only in every tab, but every image you render, and so on and so forth, you can put those in compartments. So let me conclude. Rapid tutorial. CHERI provides the hardware with more semantic knowledge of what the programmer intended. So this allows deterministic mitigation of memory safety vulnerabilities. So finally we get rid of buffer overflows, overread attacks. We provide scalable, efficient compartmentalization. So this really allows us to apply a very old idea in security, the principle of least privilege, which allows us to mitigate both known and unknown attacks. And we get enormous performance wins over process-based compartmentalization. So that's great news. And of course, we've been working with industry and the new CHERI Alliance and everybody to bring this technology into existence. And as Charlie was alluding to, one of the key things we now have is not only for CHERI, but how do we, for any security, how do we sell it? How do we market it? Who takes responsibility? And when things go wrong, who gets blamed? So I'll leave that thought with you. Thank you.